Well, hello.
Good morning, everyone.
All two of us? Three of us?
Yes,
Yes.
starting a mutiny.
We're starting a mutiny. Yeah.
So far, we got four people there. Woohoo! Lots happening in my neck of the woods. We got that, Elizabeth City is like 20 minutes away from me. In fact, my daughter is attending the school there that I used to teach at, College of the Albemarle. Luckily, they haven't been required to go to classes the last several days, but so far it's all been peaceful, now, or at least not nonviolent. I mean, they've been saying some things that would stress violence, but that's spurious members of the group. But it's crazy. I just rode over there 2 days ago and saw where Andrew Brown was shot. Uh, can't tell much from that though, not without actually seeing it. So how are you folks? And that's not windy, buddy. Hercules, chill out, buddy.
Yeah.
Hey, Wendy. I'm recording, so just I'll let you know so you don't say anything embarrassing, specifically about me.
Say everything embarrassing.
I know exactly. They want you to say everything embarrassing. Oh, did y'all notice my cup? I finally unboxed it. Check this out. One of my students gave it to me. It's a constellation mug.
Oh, I have to show you a website. I really do. I'm gonna
Yes, please.
I'm gonna ping it to
Send
you.
it to me.
I think you'll really enjoy it.
You can put it in
Okay, the
in the
chat that
chat so
just
everybody
goes
can
to
see.
you. Remember when we first started this, we could chat with the whole classroom, but no, it's
That,
now just restricted to the professor.
that's crazy. Actually, I might be able to change that.
Because it's stupid. How can we not talk to our peers? Why would you
Yeah, I
limit
mean,
us?
if someone was taking advantage of it, I can understand, but give me a break, Let the teacher have control over that.
Yeah, every classroom I've gotten into, they've limited conversation from the peers, and we're just like, well, how are we supposed to actually? This is supposed to be a college grounds. We're supposed to confer with each other from time to time.
Yeah, evidently they just changed the default, so we can still do it. I just had to put everyone publicly, so you can chat now.
Oh wow.
Well, guess what I realized after class last time?
Hmm.
I realized that I'm clearly a goober or dummy or something because I jumped into chapter 24 specifically because I grabbed the wrong textbook when I went to read, and of course it only had chapter 24. So I was thinking, well, that's okay. That's all I had to do. We'll come find out that was for the other class. I only had to do chapter 24. So I completely skipped chapter 23. So that's what decided to talk about today. But I'm also here to field questions. So does anybody have any questions?
I have no questions, and I figured you'd meant to do chapter 23.
Yeah, I'm a goober. I did have one student email me about two problems on the test, one of which was what is the wavelength of violet light, and it's got it completely backwards. So just be prepared for that. I'm going to try to change it in the bank, and that'll correct everybody's test. I did his manually,
There you
so
go.
that should be fine.
That is, I want to get a couple of things off of this website.
Gotcha.
I
Check
love
it out.
some of the stuff on there.
I will pull it up after class just because, like I said, I never know what's going to come up, but everybody else can check it out too. So, anyways, that was one error in the actual test seven. It asked, the right answer, what it expects is the right answer, is 700 nanometers. When in fact the violet end is the small, or excuse me, is the small wavelength end. So it should be closer to 400, 380, something like that nanometers. So just be advised about that. Uh, Also, if you take the redshift and add one to it, you can then multiply that by the wavelength of that you actually would normally see, and that'll give you the wavelength observed. So if they talk about the redshift of a quasar, for instance, being 6, that means you go 6 plus 1, you add 1 to it and you get 7, and you multiply 7 times the wavelength of the light that quasar would normally put out, and that gives you the wavelength that you'd observed, and it's not in the radio. Okay, I'll let y'all work out where it is if you want, but basically you're just multiplying the real wavelength that was put out by 7 to get the redshifted wavelength. In that, and I'm specifically talking about page 344 to 346. So that's another question that comes up. That one's not wrong. The answer's not wrong. It's just maybe students misunderstood what was being said. So, well, like I said, does anybody have any questions before I get started on chapter 23? I just want to cover it for completeness. It's on the large scale structure of the universe. It's kind of interesting. It's cool how, I mean, it's very interesting. It's again that cosmology area where galaxies are considered infinitesimally small point-like objects. And then you start to see, superclusters and stuff like that. And then superclusters group up to form walls and filaments. And then the walls will actually surround areas that look like they're empty, but they might just have a few galaxies in them or not very bright galaxies. And those areas are called voids. So it's the biggest stuff in the universe. In that sense, it's awesome. So I guess I'll reach a conclusion that no one has any questions. So let's get cracking on this. So here's the chapter 23, the large scale structure of the universe. And I should say, I really, really, really love this textbook. It's awesome. I hope y'all have enjoyed it as much as I have. It is actually one of the toughest in terms of the material they're willing to cover, the depth they're willing to go in, and the mathematics that they're allowing are actually is covering is quite in depth as well. So I like that, but I don't have to do any of that math, and I can still use it as a good textbook. And I think the writing's well done. So I just wanted to state that is the book textbook K. Palin and Blumenthal, 21st Century, 6th edition. I will start off by sharing the learning goals for this chapter. And the learning goals are, crap, I lost my other bookmark. The learning goals are 1, describe the distribution of galaxies in the universe. So we're supposed to describe the distribution of the galaxies in the universe. That was what I was talking about earlier with filaments and voids and walls and stuff like that. Learning goal 2 is explain how the large scale structure of today's universe evolved from the structure that began to form shortly after the Big Bang. Big clue here, dark matter is a big answer to a lot of this. Learning goal 3, describe the formation of the stars in the first galaxies. And then learning goal 4, explain how the observations of galaxies at different redshifts illustrate evolution of the large scale structure of the universe. So those are the learning goals, what we're discussing. Your book also has a nice table on page 640 that shows the redshift and the age. So that redshift is the Z that you're working it out, mathematics stuff talks about. And you'll see that if you want to see the recombination period, which is at 380,000 years after the Big Bang, that's the instant that the Big Bang cooled down enough where actual electrons could fall and be or fall into or be captured by hydrogen and helium. Okay. Before that, everything was loose particles, and therefore everything, every wavelength of light essentially could be absorbed. So no light got out, even though there was a buttload of energy around and it was producing radiation, because that is the very definition of radiation is basically a form of light in that great excess undermines various industries' Marxism rules, EM spectrum. So all that light was ambient, but it was constantly being absorbed by particles that weren't restrained or constrained in any way. It's only in quantum mechanics, it's only in constrained situations where you get allowed frequencies and wavelengths to be absorbed. So at 380,000 years, the temperature finally got to that critical temperature mark, which I seem to recall being around 3,000 Kelvin. And at 3,000 Kelvin, electrons can fall into hydrogen in orbits around hydrogen nuclei, which is obviously just a proton, and around helium nuclei, which are alpha particles. And at that point, all the radiation blows out. And that really is what we see as the cosmic microwave background radiation. Okay. It would have came out at that roughly, the Planck's curve would have a peak according to Wien's law at whatever that temperature was, which I told you I thought I remembered was around 3,000 Kelvin. And that peak is what was sent out. If you work out that wavelength by dividing 2.9 times 10 to the negative third meters times Kelvin, if you divide that number by the actual temperature, which again, I'm arguing that it's 3,000. I might have mistaken that. It could have been 3,800, could have been 2,800. I can't remember. But when you do that, you'll get the wavelength of the background radiation emitted. But as the universe has expanded, if it expanded, say, fourfold, then, and that wavelength was 10 centimeters, which it wasn't, but I'm just saying as an example, then that wavelength would now be 40 centimeters because it's done tenfold. And that's really what we see. That's why it's now in the microwave. Okay. So, anyways, this table 23.1 on page 640 gives you the Z value for various points, one of which is the recombination where Z is 1100. So that's really a huge redshift. 30 is 100 million years after the Big Bang. 20 is 200 million years after the Big Bang. 15 is 270 million years. 10 is 480 million years. And then some key dates really is there was a period of basically what they call the Dark Ages after that 380,000 years. So at Z equals 1100, basically that's the time at which this Dark Ages began. And that went on to about Z equals 9, maybe Z equals 8.9 or something like that, because it's about 550 million years after the Big Bang. And the reason why that was a dark age is the ambient light is only light coming from the universe itself. There has not been any stars made at that point. Okay. No stars, no galaxies. So there's not any light coming from cosmological objects. It's just light from the universe, from radiation, whatever, not from actual stars and galaxies. So that's the dark ages. And then at the 550 million years mark, we start to see stars that have formed and galaxies starting to form and stuff like that. So that's what's really awesome about that table. If you go to zero, obviously that's 13.8 billion years after the Big Bang, Z of zero. A Z of a quarter is 10.5. A Z of a half is 8.6 billion years after the Big Bang. And a Z of one is 5.9 billion years after the Big Bang. That's a good table to refer back to as you're reading the textbook. I literally basically put a post-it note stuck in there as a bookmark, and every time it mentioned a redshift, I would slip back and forth into that page to read it. So that's a good thing for you to do as well. So this is also one of the coolest pictures ever taken. This is the Hubble Deep Field, and remember, this is a small area of the sky. What I've suggested is it's an area of the sky about as big around as a wedding band. If you look through a wedding band sitting on the end of the pier at 17th Street or whatever that road is that pier's on downtown in Virginia Beach, the waterfront. If you stood at Atlantic Avenue and looked through a wedding band on the end of that pier, that's roughly how narrow of a cone of sky that the Hubble Deep Field is zooming in on, and still it found on the order of several thousand galaxies. Every one of these things that don't have this characteristic cross on it is in fact a galaxy as opposed to a star. Stars are pinpoint objects, so they diffract and cause these little pinpoints. So there's a star, there's a star, there's a star. Everything else is a galaxy. And that just gives you an idea of how immensely packed the universe is, because that area was taken of one of the darkest areas they could find. So they looked near the Big Dipper, Ursa Major, because that's near our north celestial pole, and Hubble's orbiting the Earth. So it had to, in order to keep from missing it because the Earth would get in the way, it had to shine or aim at something above the North or below the South Pole. So what it chose was an area that looked pitch black in the constellation Ursa Major, and it basically did the equivalent of leaving the aperture open for about 11 days. So after 11 days, this was the light it collected. And that area being black means, from our standpoint, that's probably the least packed, one of the least packed areas that exist. But we've done it on other areas too, and the numbers keep coming back. So this is how we know that the universe has 1 followed by 11 zeros, galaxies in its observable part, which is about the same number as there are stars in our galaxy, 1 with 11 zeros after it. So that's a really cool image. And what you need to remember when you're looking at these images in astronomy, the farther you look away, the longer back in time you're looking. Okay. So if you look at something that's 10 billion light years away, you're not seeing it as it looks right now. You're seeing it as it looked 10 billion years ago, which is just 3 billion years, 3.8 billion years after the Big Bang. So we we are sort of cursed because we can't see things in real time far away, but we're also blessed because we can see things as they were happening back in history. And that helps us form an idea of how the cosmos became what it is today. So when all we have to do is look farther and farther, get closer and closer to that, let's say to that 550 million years after the Big Bang. So closer and closer to a z equal to 9. As we get closer and closer to that z equal 9, we are seeing things, galaxies and stars as they're just starting to form. In that case, it would actually be just stars as they're starting to form, not even galaxies. We might be able to make use of seeing the dark matter clumps by the gravitational lensing that's taking place in that. And from that, we can put together sort of how galaxies are forming. And it turns out, unlike stars and star systems, which is a top-down structure where basically the big things form out of the first and then create other smaller things. Galaxies seem to form from a bottom up way, so that basically you get the little bits and pieces all together, and then that forms the bigger thing. So that's what you're going to learn in this chapter as you read. So collections up to several dozen galaxies are called groups. And then once you get several those groups together, large collections are called clusters. They can be tens of thousands, for instance, of galaxies. And then galaxy clusters contain, as you're familiar with, most things contain way more dwarf galaxies than they do elliptical galaxies, and even lesser spiral galaxies. But often the larger galaxies, giant galaxies, have the vast majority of the mass in the actual clusters and groups. And then clusters and groups bunch together to form superclusters. We are in, for instance, the Laniakea supercluster. And if you look at the photo, let me see what page that is. It's going to come up on the slideshow. I already saw the slide earlier. But if you look at the figure 23.2 on page 636, you'll see that, in fact, those white dots are supposed to be actual galaxies as they're moving towards what we used to think was the great attractor. It turns out to be the center of mass of the Laniakea supercluster. The supercluster includes the Virgo cluster. Our Milky Way is in a small part of it. And then, of course, the distant away is the Coma cluster and the Shapley cluster. And what you're looking at there, those blue spots are really voids, and those green spots are actual galaxy clusters. Okay, so that's a really cool thing to keep in mind. They're going to show you the picture in a second. What we've managed to look at is a distance. And in fact, we can look sort of two ways. Remember, our galaxy's got this huge disk, right? We're like a blueberry and a blueberry pancake. And the blueberry can see above the pancake and the blueberry can see below the pancake, but looking into the pancake is really hard, and we can only get images on very specific wavelengths there. So what we do is we sort of look out in one area and we get this little slice, and then we can look out the other area and get another slice, something like that. And that's basically pretty much all we can see with the universe. But we can then, knowing distances and angles and stuff like that, we can put together the geometry, not unlike figure 23.2. So the redshift surveys reveal the distribution of clusters and superclusters. The universe is actually sort of like a sponge or even a coral, or you can even think in some sense that it's like a bunch of bubbles stacked on top of each other. So if you've ever seen the big bubble that's made when you make a bubble bath or maybe washing dishes, the matter, the clusters of galaxies are sort of along the edges of the bubbles, forming walls, and in some cases maybe between three different bubbles, where a bubble's here and here and another here. That's just a thin one-dimensional object. That's a filament. And then that's where all the galaxies are. And the opening in the bubbles would be the voids that we were talking about, which may or may not have galaxies in it, but they're certainly not very bright galaxies. Okay, so that's the porous structure you're talking about. You can also say it's a sponge-like. I like the bubble analogy because I can picture it and have enough experience with it where I can see, hey, these two bubbles coming together right here have created a two-dimensional structure that looks like a wall. And in fact, if I put a third bubble under there, then it reduces that two-dimensional structure to a one-dimensional structure, so I can see the filaments. That kind of works for me in my innate or fairly decent but not great ability to see in 3 dimensions. The superclusters are often extended and filamentary with voids in between. This is called the large scale structure of the universe. There's the photo I was referring to, figure 23-2. As you can see, these green things are actually superclusters. These white things are galaxies that we're sort of tracking on the path that they're moving through. That blue dot is our Milky Way galaxy. Okay. It also said something about the orange dot. I'm trying to remember what that was. The dark blue dot is us. The white lines indicate movement of galaxies toward the center of the supercluster. The blue area voids. Red dots indicate the Virgo cluster. I think they're talking about not that necessarily thing. I don't even know what that is. They're talking about this. That's what it was. Okay. So yeah, they didn't actually say anything about what that one is. But these little red guys right here that you see in that area, that's the Virgo cluster. So clusters and superclusters interact with each other gravitationally. There's also a peculiar velocity. This was kind of hard to wrap your head around. I think that's why your author chose to just do sort of one sentence. But peculiar velocity is the velocity with respect to the cosmic background, microwave background radiation. Okay. The local group has a peculiar velocity due to pulls from the Laniakea supercluster. So once you set yourself relative to that microwave background, then you can see yourself, the Milky Way galaxy in this case, as how it's moving. And that's what these white lines are reflecting, how we're all moving. And they thought, like I said, it was this great attractor, meaning there was some super massive supercluster or some supermassive galaxy all by itself that was so big it was calling all these things to the center. We've since discovered, after mapping all this crap, that basically the attractor is more or less just the center of mass of the supercluster system. Okay. So this is where you can see, for instance, the Milky Way galaxy would be like along here, and there's parts here and here we can't see because of that. But when you put all this out, you get this really nice structure. This is the Great Sloan Wall, named after the Sloan, the person that made that the telescope's also named for, that did these observations partly. These are some of the voids we're talking about, these dark spots. If these things are two-dimensional, then they're walls. If they're one-dimensional, then they're filaments. That's pretty much what it is. And the most awesome thing about this is we can use our modern ideas of cosmology and how we use this bottom up construction of the universe, specifically galaxies and galaxy clusters and stuff like that. And we can use the laws of physics to write code and run it on supercomputers, and the supercomputers can spit out what would we expect to see if we are right about how these superclusters and things formed using dark matter and whatnot. And you will see actual simulations results that look exactly like these things, as we'll see in a second. So that gives us a great deal of confidence that our cosmologists know what they're doing and have stumbled upon and I shouldn't say stumbled upon, that sounds like an accident, but have figured out roughly how the universe came into being. So as you know, there are 8 to 10 times more dark matter than normal mass in galaxy groups. In the interstellar space is not quite that high. So the ultimate result is that about 5% of the universe's mass is stuff that we're familiar with. It's stuff made of protons and neutrons and stuff of that sort. They call it baryonic matter. That's another name within the industry or within the academic world that we call it. And then about 5 times of that makes the mass of the entire universe. So 5 times 5% is about 25%. And then the remaining 70 or so percent, then that 25 could be a little higher. That 5 could be a little lower than 5. That 25 could be a little higher than 25. And then the 70 could be a little larger than 70, of course. That's the dark energy. Okay, so we really are studying a 5% universe. But what we find is that dark matter evidently plays a key role in creating galaxies. and it probably played a key role in helping star formation. But the thing is, it doesn't contract so much on that scale. It turns out dark matter contracts on large scales, and it has a pressure type thing that's formed as a result of the motion of the dark matter, so that it reaches an equilibrium. But that equilibrium is quite large, and usually on the order of the size of clusters of galaxies as opposed to individual galaxies. So they stop forming, but their contraction of the dark matter is enough to get the matter moving, and then the matter can actually not only contract, but it can also radiate some of its energy away and contract further down to make the smaller objects that are the individual galaxies. There's hot X-ray emitting gas that can be bound in clusters, and it's only due to dark matter's added gravity. In other words, that added gravity gave it enough speed where it reached temperatures that Wien's law suggests would peak in the X-ray. Okay, so it's really high energy stuff, but it is quite ephemeral. So it's again sort of like the corona of our sun, where it's not. I mean, it's hot enough. It's 1,000,000 Kelvin, 2,000,000 Kelvin, stuff like that. But it's not really dense enough for it to harm you if you actually were to stick your arm in it. No more than sticking your arm in a hot oven. Other than touching the sides of the oven, it's not going to bother you. Maybe it'll melt some hairs on your arms or something like that. I'm not sure. So we actually are able to view these things and look for this dark matter using gravitational lensing. That gravitational lensing, for instance, if you have a cluster of galaxies, or maybe even you have dark matter in here, then light coming from this distant object will come up and it'll try to go straight, but space is warped due to general relativity. So it'll go as straight as it can in the crooked space, and the crooked space will send it back here. And what you'll see is these little arcs like here. So this arc could actually be a sort of a focused, flattened image, magnified, of something back behind this mass. And if you find the center of these arcs, that's roughly where the center of mass of the big thing is, the thing that's causing the gravitational lensing. The gravitational lensing by the galaxies and galaxy clusters produce bright arcs of deflected light. They're called Einstein rings, for instance. The greater the deflection, the greater the mass. That can allow us to figure out what mass is there. Gravitational lensing reveals the amount of dark matter in the universe. And just as stars form around gravitational instabilities in molecular clouds, so remember the molecular clouds are basically the ones where we formed heavy elements, which in cosmology and astronomy, heavy elements means anything heavier than helium, which is basically everything: lithium, beryllium, boron, carbon, nickel, sodium. All that stuff is quote unquote heavy elements. But it formed around gravitational instabilities. But it seems the galaxies started off with gravitational instabilities due to dark matter as opposed to due to regular matter. Dwarf galaxies formed first, with larger galaxies forming next, and then clusters, and then superclusters, and then superclusters grouped together to form filaments and walls, forming in later processes. This is called the hierarchical clustering, meaning it started from small, built a bigger thing, built a bigger thing, built a bigger thing. That's the bottom up construction that we're talking about. And that's also, by the way, just, it's not that relevant, but it's kind of interesting to talk about. That's the way we built our space shuttle. And when the Challenger, I think Challenger was the first one, blew up, Richard Feynman was put on the committee to actually research what happened. And he made a whole appendix to his report, and he negotiated with him to get his whole appendix put in there, mainly because he was sort of held back, like people didn't want him investigating things on his own and stuff like that, and people were doing too much meeting type stuff as opposed to actually getting work done. So he just went off on his own and did his own thing, and really discovered what the problem was, and then probably ticked off a bunch of politicians. But anyway, he got that done. He got his piece put in there. And what he was saying was, we built the space shuttle on a bottom up way. So we had all these little problems we had to solve, and we solved them. And then we'd go to this other problem, we'd solve it. And from that, we had all these little bits made up. And then built the shuttle out of that. Well, that's great. And that's the way you discover how to do things. But now that we've done that, we should go back and look at it from a top-down standpoint where we can actually uh, build things and pull items right off the shelf instead of having to machine every part and stuff like that. You can build prototypes and like the Apollo 13 movie, you wouldn't have 12 different types of filters so that if one goes out, you can't use another. No, you'd have something from a reverse hierarchical structure working down. So just to give you that little historical tidbit, that's tells you a little bit why uh, NASA had a space shuttle program that wasn't the most super efficient, and why the we wanted the private sector to take that over, so that they could then, not on our dime, but on their own dime, figure out how to make it better and more efficiently. Because it was sort of unethical for us to go back and rebuild a whole new thing, and it would be, not necessarily very popular for us to do so when companies could do that and make a profit off of it. So anyways, in order to have this happen, the universe must not have been entirely uniform. And in fact, here's the problem: when you got gravitational instabilities, meaning high density areas in various places, as the universe expands, those high density area differences become even larger and more prominent. So in order to have this happen, the universe must not have been entirely uniform, must have been had denser regions which were amplified over time by gravity. The density variations in the cosmic microwave background radiation from normal matter are not great enough for the larger structures to form. So, in other words, when we look at that Kobe or W map, the speckled robin's egg, as they called it in the video, when we look at that speckled robin's egg, we see very small differences in everything. In fact, the temperature's only changed by 10 to the negative fifth, roughly, Kelvin from the hottest to the coldest. So it's a really small variation. Those small variations weren't enough to create galaxies and stuff. So we now had to conclude that it was the dark matter. So we had all these different ways of seeing the dark matter and confirming our results, but basically they all point to the same thing. Dark matter must have helped. So dark matter, not made up of neutrons and protons, non-baryonic matter, in other words, must provide the clumpiness in the universe for structures to form around it. So you can see here, here's a normal matter and radiation, and here's dark matter. And as you see over time, gravity, as the universe expands, will sort of make this flatten out. But it was the dark matter that was actually able to hold it together enough to keep it from completely going to no difference in gravity whatsoever. So clumps of dark matter, normal matter, and radiation emerged from the very early universe. The pressure of radiation smooths out the normal matter clumps as the universe expands, leaving behind the dark matter clumps in a far more uniform background of normal matter and radiation, and very slight irregularities remain in the observed cosmic microwave background radiation. Whew, that's a lot of words. So the dark matter is characterized by its average speed and its composition. There's really just two types. There's cold dark matter and there's warm dark matter. Cold dark matter moves slowly compared to C. Its candidates are unknown elementary particles like the axions and photinos. So the photino is a weird thing because Tino, you probably recognize, means little something, right? And so this would be the little photon. But photons have basically zero mass. This one's going to have mass literally thousands of times heavier than the proton. And axions are other sort of large small particles. Again, large compared to electrons, of course, but also even protons. And then the hot dark matter moves very rapidly. It might be neutrinos, that we at least think that's part of the contribution is coming from neutrinos. But only cold dark matter works to form the smaller scale satellite galaxies. So when we're looking at these little galaxies, it's the cold dark matter that really comes into play here, not the warm dark or hot dark matter. So at recombination, remember that's the 380,000 year mark. At recombination, dark matter clumps exist in a relatively uniform background of normal matter and radiation. A few million years later, the gravity is slowing the expansion of the dark matter clump. Gravity is slowing the expansion of the dark matter clump, and within a few 100 million years, the clump reaches its maximum size. Normal matter has been pulled into the clump. So once the normal matter is pulled into the clump, then that can make the gravitational instabilities that we need. Normal and dark matter continue to collapse until the dark matter can collapse no further. That's where that basically that pressure due to the motion of the particles is counteracting the gravitational attraction of itself, and it's in many ways above the expansion abilities of the universe. So you don't have to rely on the universe to expand it, or you're not going to have the universe expand it. Normal matter, which can cool by radiation, continues to collapse at first into smaller clumps, and those clumps merge and they form galaxies. Okay, so that's really the model of how galaxies form in dark matter clumps. Uh, the first stars potentially formed in dark matter mini halos. So what we think happened for the very first generation of stars is we didn't have a lot of the mechanisms that we learned about when we were learning about low mass and high mass stars. We, for instance, can't do a CNO cycle, right? How are you going to have the CNO cycle as opposed to the proton-proton chain in the early universe when you're literally, one of the first stars being formed? In other words, you're a star being formed, or imagine a star being formed before any other stars died. If that's the case, then you only have at your disposal hydrogen, helium, and maybe a little bit of lithium, right? So there's no way in heck you can use the CNO cycle because that requires C, N, and O, carbon, nitrogen, and oxygen. So there's an entirely different mechanism. And we think that mechanism was basically dark matter mini halos. So you imagine sort of spherically shaped blobs of dark matter concentrating neutral hydrogen. The models predict that the first stars were hot, massive, and short-lived. So most stars would have been really, really big. And our models, at least for the CNO cycle, suggest that they might only live millions or tens of millions of years. The second generation of stars would have formed from these as well, and low mass second generation stars could potentially be seen today. We have not to date found any stars that have only hydrogen and helium. In principle, that's something I think we should see, unless we find out that theoretically there's some reason that low mass stars, low enough to still be living, say zero point 0.8 solar masses, a zero point 0.8 solar mass star has a lifetime that's longer than 13.8 billion years, so they should still be around. If we find some reason why that first generation of stars couldn't form stars of that small size, then that would explain why we can't see currently any stars with just hydrogen and helium and maybe a little bit of lithium in it. That being said, we do find a buttload of stars. We've hundreds of thousands of them where the stars are light on heavy elements. In other words, they have very little heavy elements, nowhere near as much heavy elements as we have in modern day stars that have been formed. I say modern day within the last billion years. Okay. So the second generation stars would have formed from these, and low mass second generation stars could potentially be seen today. I think we have some candidates for second generation stars that we're looking at. Your book mentioned one of them. It had a weird name, but I can't remember what it is anyways. So the second generation stars were the first low mass stars, as best we can tell. That is sort of our only explanation we can have for that. The first galaxies most likely formed from the merging of many halos of second generation or low mass first generation stars. They were shaped by radiation and the first generation stars, heavier elements, and black holes. So we are actually seeing at that 550 million year mark, not only are we seeing stars being formed or having been formed, because we see the death knell of stars. We see black holes, we see degenerate stars, which would be neutron stars, white dwarfs, black holes are beyond degenerate, that sort of thing. So we are seeing those. And according to one theory, the first galaxies formed a few hundred million years after the Big Bang. That is an idea. We're not really sure. And basically what it is those first galaxies, if they formed, would probably be irregular and maybe starting to form into elliptical, stuff like that. Spiral galaxies, we certainly think were the last ones to form, which is weird because the spiral galaxies are so beautiful and well orchestrated. You'd think over time they'd had so many collisions that the spiral galaxies would be old ones, but it seems that the spiral galaxies take quite a bit of time to develop. A few high redshift galaxies have been discovered. These galaxies are 20 times smaller than the Milky Way. Again, this shows us that we're probably right, that small galaxies formed first. These are the youngest galaxies discovered, and they provide insight into how the first galaxies formed. Galaxies appear to have evolved hierarchically, like we were saying before, from small to large. So small protogalactic fragments merge into larger ones, making what we call ultra faint dwarf galaxies. And they would be obviously very faint, meaning they don't put out a lot of light, maybe as much light as 100 to 1,000 solar masses, that kind of thing, not very big. The ultra faint dwarf satellites of the Milky Way may be leftover ones. So remember, our Milky Way is in a group called the local group, and that local group has a couple dozen galaxies in it, the vast majority of which are dwarf galaxies, and some of them are ultra faint dwarf galaxies that could very well be some of the first galaxies ever created. Galaxy formation has many of the same processes as star formation. They both start with gravitational instability. The problem, though, is, like I said, dark matter stops collapsing once it gets a much bigger size than a typical star, whereas star matter and molecular clouds continue to collapse until they get the size of the stars. So the only the mini halos of dark matter are that influential on creating stars. The other blobs that create galaxies are not playing roles in star creation. Fragmentation also occurs, although the order is opposite. Of course, you take something big, you break it up into smaller parts. Uh, what we're talking about there is like when you're talking about the nuclear, or excuse me, uh, the creation of the solar system. Basically, we're seeing that this large blob, nebular cloud, if you will, has some rotational axis, and then conservation of momentum makes it flatten out, and then the individual parts that would be of a whole disk, making a whole disk, that whole disk breaks up into small fragments that become, in our case, several planets, but in other cases, uh, several stars. So that's the case. Someone mentioned they had to leave early. Yes, Melvin, I addressed early in the video, by the way, your questions, and I put in comments in the actual test you took. So you can open up the test, and you'll see my comments about the questions you asked me about in your email. So compression is another thing. Remember, compression, things are falling down. That's actually compressing the inner gas, which ultimately becomes the core of the star, but is at that time the core of the protostar. That causes heating, basically because when something falls in, it converts its potential energy into kinetic energy. As the average kinetic energy, translational kinetic energy of the molecules and atoms increases, that's the very definition of increasing temperature. Once it reaches that critical 10 million Kelvin, then hydrogen can confuse into helium. Of course, once you meet that 100 million Kelvin mark, then helium can fuse into carbon and other things. But those are the first two marks. You have to hit the 10 million Kelvin mark for a protostar to become a star, and you have to hit the 100 million Kelvin mark for helium to fuse into carbon. And they both have a role for angular momentum. So the angular momentum can form the disks of the galaxy, but it can also form the disks around the star systems, which are, like our solar system. The end product is centrally concentrated material with a surrounding disk. Unlike stars, most of the material in the spiral galaxy remains in the disk instead of concentrating in the center. So that's one of the major differences between that sort of metaphor, if you will, of the formation of stars being a metaphor for the formation of galaxies. You know what a metaphor is? For grazing cattle. That's what a metaphor. Sorry, that's an old English teacher I used to have. Used to do this Randy Redneck thing, and that was one of his quotes. I just thought of it a second ago. So early in the universe, when the universe was much smaller, obviously the mergers were common. You can see this is a logical progression, and this is really, Hubble's classification system of galaxies: spirals, barred spirals, ellipticals, and then very few irregulars, which are obviously they're irregular because they've been had the crap kicked out of them by other collisions. But 11 billion years ago, you'd see spirals looking like this that now form to this, and you'd see barred spirals looking like this that now form into this. But you'd see ellipticals looking like this to this to this. And notice the difference. They're more yellow here, they're more white here. meaning that some of the more bigger, hotter stars could actually form, even though they're short-lived. So early irregular galaxies are emerging galaxies, and prior to 11 billion years ago, there were no galaxies with visible structure. So it probably took 2 to 2.8 billion years to actually get a visible structure due to the galaxies. And then 4 billion years ago, galaxies were much more irregular. Supermassive black holes and galaxy bulges appear to have grown together. So the supermassive black holes, one of the things people thought of was maybe these initial stars coming together in these mini halos and other dark matter things could have been the seeds for the supermassive black holes. But it seems like, as best we can tell, the supermassive black holes aren't old enough to be that. So that's probably, maybe it's a 50-50 thing, but it might be more like a 70-30 thing, where 70% of the people think that the black holes did not form that way, and the 30% say they did. But again, supermassive black holes and galaxy bulges appear to have grown together. Hierarchical merging most likely triggered star formation, which peaked when the universe was about 2 to 3 billion years old. So if you look at star formation, as best we can tell from experimental results, it turns out that basically after the Big Bang, around 3.5, or excuse me, 2.5 billion years after the Big Bang, that was when the peak of star formation occurred. And ever since then, star formation has been decreasing, which is as you'd expect. If the universe is really expanding, that means the matter is getting farther and further away from the other matter. And how is the other matter going to, form stars if it's so far apart when gravity is so weak? So that's the case there. Here's some pictures of young galaxies and mergers. So you can see, this is clearly running into or just ran through a galaxy. These two are about to run into each other. These two seem to have already collided and have some effects. Same thing with all this. So these mergers are observed to happen often, especially in dense clusters. And elliptical galaxies can be made by mergers of spiral galaxies. As you can see, when spiral galaxies uh, leave one another, they lose a lot of their spiral nature. Like looking at this one, you could see, for instance, this one going on to become just a elliptical collection of stars with little or no gas in it, because this one sort of stole most of the gas that was in there. So the galaxies so the galaxies form early. The structures, the voids, the filaments form later. Again, that's from a bottom-up standpoint. We're not saying that the galaxies form first before the stars. We're just saying that the smallest part of the galaxy structures, the groups, the clusters, the superclusters, the galaxies would have formed first, and then they would group together to form groups, and then they would group together to form clusters, and then they would group together to form superclusters, and then the superclusters could form together to make filaments and walls, and then of course the walls would surround voids, and sometimes filaments would surround them as well. So this is amazing. This is what I was telling you about earlier about simulating the creation of the cosmological structure of the universe. This top one's an actual image that we've created based on all the galaxies we found. So it's like that first image, those first two images we saw, where it was that single wedge and then it was the two wedges. It's just like that. It's just another piece of data like that. And it's listed as 200, 400, 600, 800 megaparsecs away. And they did a calculation. It's called the Bolshoi simulation, and that Bolshoi simulation produced something that looks eerily just like the actual data. I mean, look, it's got voids, it's got clusters, it's got filaments and walls. This is really surprisingly similar. So simulation with only certain combinations of mass, cosmic microwave background variations, types of dark matter halos, and values for the dark matter energy produce structures like we observe in the Sloan Digital Sky Survey. So basically, we're just taking the data that we know exists and taking the laws of physics that we know, including relativity, general relativity, Newton's laws of motion, that sort of thing, and quantum mechanics, and putting all that together and then saying, okay, well, what would happen if we let this, cluster of crap that I just threw in the computer run through its life processes? Well, this is what would happen. And lo and behold, this looks a lot like that. Ergo, we must be onto something. So the fact that simulations match the data so well gives us confidence in our models. So future of the universe, this is a little depressing. The good news is we're talking billions and billions of years from now, so we don't have to worry about it really. But based on our current ideas, the universe will probably expand forever. In 10 to the 14th years, remember we're at 13.8 billion. A billion is 10 to the ninth, so we're talking 10 to the 10th years is where we are now. So another 1,000 times larger than what's already occurred. The last molecular cloud will collapse, forming the last stars. So we're going to get basically what we've had already times 1,000 before this starts to happen, and that would be our last generation of stars. It will only take about 10 trillion more years, so that's 10 to the 13th, or excuse me, yeah, 10 to the 13th more years for those last stars to die out. And again, they're taking into consideration literally the lowest masses of stars that live the longest. And that will leave white dwarfs, brown dwarfs, and neutron stars, basically the degenerate matter. And in 10 to the 39 years, which is really huge, you're talking one with 39 zeros after it, normal matter will decay via quantum effects, leaving only black holes. So basically, even matter, even atoms eventually start to fall apart, and that's the problem. That's the very end part of what Beyond the Big Bang was talking about. And then after a Google of years, and that's not spelled the way we spell Google for the search engine, Google. I think it's spelled Gogl or maybe Googl. I can't remember, but it's basically 10 to the 100th power is a Google, and then a Googleplex is 10 to the Google power. But anyways, in a Google years, even the largest black holes will evaporate. And basically, with that, when everything's evaporated, you don't have any matter far enough or close enough together to interact with the other matter, and you end up slowly cooling off to that 2.7 Kelvin that the universe seems to be at, which might even be lower by then, of course. So it basically is going to be what we call a heat death of the universe. Like there's without heat transfer from one thing to the other, nothing occurs. So that's really the ultimate end of the universe. The universe will be structureless and empty except for any residual uniform dark energy. So literally, the dark matter is going to be separated, and you just have dark energy left. So that's it. That's the entire large scale structure of the universe chapter 23. Scientists, this process of science. I hope you've been reading these throughout the semester. I haven't been covering them in class, but all of them are pretty good. And this one was a decent one. So scientists do not have the luxury of ignoring evidence that not to fit current theories. Yeah, we can't just say, "Oh, that's biased," right? If we're going to make such a claim that that evidence is bad or biased or something like that, then we've got to show that it is. And more specifically, it's more up to the person that's showing it that the method they used was on the money. And if the method was they used was on the money, then someone else should be able to replicate it. If someone else can't replicate it, we can start to think of it as not useful data, and therefore we don't have to use it. But other than that, the vast majority of data we just have to take. We have to say, well, this is what the universe is telling us, and therefore we're going to have to use it. They must see being wrong as an opportunity to learn and as a challenge to try harder. So that is a really important thing. I try to teach my students that, a bad hypothesis, quote unquote, a bad hypothesis. There's no such thing as a bad hypothesis. We should say something like hypothesis that proves untrue is almost always the most valuable hypothesis, just because the hypothesis that proves untrue leads us to learn so many other things. Because if we made the hypothesis that was untrue, we thought something about the universe that was not, and therefore we learned something new that was about the universe. So anyways, I'm going to call it there. You can see all sorts of calculations in the work it out. This is where I was telling you, if you add z to 1 and then multiply it by the wavelength that it's supposed to be, then you'll get the actual observed wavelength. And you can see from this calculation, for instance, for Melvin, the visible light that was put out by quasars at a redshift of 6. 1 plus 6 would be 7. So 7 times that visible wavelength would put us into the, let's say, 850, or excuse me, about 8,500 nanometers, which is in the micrometer range, and the micrometer range is definitely in the infrared. So, anyways, that's it. We're done. Anybody have any questions? If not, you're free to go. If so, stick around and I will answer them. Anyone? Anyone? Remember, our exam is Thursday, final exam Thursday. It will be taken at this time at 11 p.m. You have to use Respondus. You have to use Respondus Lockdown browser, and you have to use Respondus Monitor. And if they don't work on your computer, then you're going to have to find the time to do it at the testing center, and you should test that already. So go back and test the Respondus test for the
Does it just
midterm.
open Thursday or is it due Thursday?
What's that now?
Does it open Thursday or is it due Thursday?
No, it opens at 11. Well, put it this way: if someone tells me they have to go to the testing center to take it, then I will put it on the internet earlier so that they can take it during a certain time period. But at 11 o'clock Thursday, you're supposed to log in and take it right then.
This Thursday or next Thursday?
Next Thursday, yeah, not
yes,
yeah.
the 6th.
Oh, excuse me, not Thursday. I forgot I'm on Wednesday. So next Wednesday. I'm sorry, I said Thursday.
Next Wednesday. So the 5th, people. The 5th is the final.
Yeah, the 5th is final. Thank you. I forgot. Sorry about saying Thursday. That made it even worse. God, that's terrible. So yeah, but if anybody needs to take it on Monday, you let me know. I can probably work that out. But everybody should be ready to take it Wednesday. Anything else?
Anyone? Wednesday the 5th, people. The 5th.
Wednesday the 5th. Thank you. Oh, Amani, I got your email and I did change everything. I did the test the first day, but excuse me, the day after I talked to you, and I did the homeworks last night or yesterday morning. I can't remember. So they're all set up and ready for you to roll, Amani.
Okay, I did see everything. Thank you.
No problem. Well, you folks have a good one. Have a wonderful weekend. Next week's the last week of school, and life will be quite different for a little while. I think we get 2 weeks off before the summer semester starts.
You want us to show up Monday?
Classes. What's that?
You want us to show up Monday?
You don't have to. I will log in to see if anyone's there. That's just going to be your chance to ask me more questions.
Oh.
Okay, so if you've been working practice tests and you need some help, that's a good time to ask me about it. The practice finals up, right, Autumn?
I did not see it this morning.
Let me double check with that. I'm pretty confident I already made it and posted it, but if not, it'll be posted today. Let's see. I'm going to my modules.
Yeah, it's not up right now.
Okay.
It's not up right now. Okay.
No.
All right. Then yes, it's just a matter of me clicking a button to turn it up. Yep. I'm going to put this one up right now. I might change it later just because I got to double check, make sure this is the right form. But it says PT _ final exam.
Yeah, I see the practice test.
Okay, actually, I can tell already it's wrong. It's only got 90 points instead of 100, so something's going on with the questions. Let me see.
Yeah, the same thing happened with practice test 7, chapter 19 and 20. It's like 29.5.
Yeah, and this one seems to only go through chapter 21, so that's what I need to do is add the additional chapters. But yeah, it's only got 90 points, so I got to add 2 more questions, 5 points each. All right. So yeah, you can take it now. It's not a big deal, but I'm going to add things to it. I would recommend maybe you wait a couple hours before you take it. I'll have it fixed in a couple hours. That way you can get the full thrust of all the awesomeness of my class.
I don't want to hear about the full thrust of the awesomeness of your class.
Yeah, that was an unfortunate characterization.
Wow.
All right. Well, I
Professor.
guess I'll let you guys go. Amani, do you have any questions on?
Yes, I had a quick question, real quick.
Okay.
I wanted to ask you because I emailed you about the using the web lab because it was locked for some reason. And I turned in the wrong document and I wanted to resubmit it and just turn in the right document because I actually turned in the explorations lab, which was the lab right below it. I
Gotcha.
turned that into both of them.
Okay. So is it still available, or do you need me to like open it up again so you can turn it in?
It's locked for some reason. It said it was locked around March 24th.
Okay.
So
And
I
which
just wanted
one's
you to
this?
open it back up.
Is it just called? Well, for starters, is it in the Astro Points area, or is it in like week 14 or 12 or something?
It's not in the Astro Points area. It's in the lab. It's in the lab module.
Oh, the lab course. Okay, gotcha.
Yes.
All right. I will check what that is. Do you know what week it is? So it might be quicker for me to find it.
I can pull it up really quick. Let me go get my phone real quick.
I'm going there too. So,
Okay.
but yeah, I will do that immediately so you can get that turned in. And so I don't forget. It's probably the bigger reason. So 8, there's 13, 10, 9.
Hello?
Using the lab, is that week 9?
Hello? Hello? Can you hear me?
Yeah, I don't know why. Can you not hear me?
I think that the connection just got lost for a second. I asked you a question. Did you hear the question? Because
Yeah,
I think that, what did you say?
you asked me about the turning in. I'm now on module for week 9 in the lab course. Is that
Yes.
where it is? The using the web?
Let me put,
Crap, it
yes,
just
it
lost
is week
everything.
9. And it's 50 points. I accidentally turned in the explorations under it.
Gotcha. That's weird.
And are those considered 2 different lab grades? Or is that considered 1 lab grade? Like, because I
both of those are 1 lab grade. Yeah, you got to do both of them to get credit for lab for that one.
okay.
I think that's how I did it. Yeah.
All right, I did do both of them. All right,
Okay.
and
I
that was
might
it.
split up into 2. I'm not sure. Okay, I'm going to week 9 and I'm going to reopen that up. For some reason, you're right. The connection's not very stable. It just kicked me completely
Going
out,
in
and
and
I got to
out.
go back to this module again. But yeah, I'm going to set that up right now.
Okay,
Using
all
the
right.
web. I'm in lab. March 30th. It said it would close, and that's the one you want me to open, hopefully.
Yes, sir.
Okay, I would do that.
All right.
Have a
Thank you,
good one.
Professor.
You're welcome.
You
See
too.
you,
Take
Monty.
care. Bye.
Bye-bye. You still there, Autumn? Looks like you're not. That's good.